A lot for introduction. As you said, my name is Jacob Gayles, and what I'm going to talk about today is this transverse, transport, and topological magnetic systems. I'm a postdoc at the Max Planck Institute, which is this for chemist physics Westernstoffe, which is pretty much for chemical physics of solid state, or in this case, direct translation is hard stuff in this case. But to continue, I would just give a reiteration of what Bill introduces, where I started my bachelor's in Cal State University Northridge, which is here. And then from there, during the summers, I came to Princeton for our RU program. This is where I met Bill. And after that, I started my graduate studies in physics, studying spintronics. And spintronics is a study of electrons and their spin and how they evolve in different magnetic materials. From there, my PhD advisor got a job offer in Germany, and so he asked if I wanted to go with him, and I said yes. At that time, I didn't like Texas so much. So there, and I went to Germany, and there I continued my research and developed collaborations with different groups, and so I continued in Germany at the Max Planck Institute as a postdoc, where I am a theorist in a primarily experimental group. So there's about 10 theorists for about 80 experimentalists. And so there we have a lot of collaborations, and we work on a lot of experimental problems and how to solve these. So this is what I mostly would talk about today, but first I want to give like a bit of an introduction into the field. Okay, I think most people here are math, right? So the first thing I want to talk about is spintronics, and this is the idea of taking the spin of the electron and coupling it to the motion of it. And so this is this picture here where you have the spin of the electron. And already from the beginning, I think you will understand a little bit about physicists, because this picture right here is wrong. So the electrons actually do not look like this, and they don't have spin like this. And one of the things that was found out was this was called the Stern-Gerlach experiment, which is from 1922, and this is actually the first experiment of spintronics. So what happens is if you put a beam of electrons through an asymmetric magnet with north and south poles, they will split. And what the people thought originally was that you just have this, can people see on this board over here? People thought the beam would show up just like this across. And what happened was they got two beams split. And what this is actually the quantum nature of the electron. So it has a spin of plus or minus 1/2. So it cannot take any values in between in this case. And what they actually used was silver ions instead of electrons. But to continue, what really boosted the field of spintronics was what's called this giant magnetoresistance. And this is where you have two magnetic materials, and when they point parallel, the electrons are allowed to pass through, and as you switch it, if you flip one upside down, then there's no electrons that pass through, and so you have two states of resistance. And this is a huge resistance change, more than 50%. And this is what's been used in the current hard disk drives and also for things like iPhones, and this is what allowed for to store very dense information into these systems. However, now with more and more information coming, you need more and more memory, and so a lot of the ideas of spintronics is how can you increase this and decrease the heat and also increase the information in a cost-effective way. And so one of the new ideas that has come out of this same similar device is what's called the spin transfer torque. And so instead of just having them exactly parallel, if you just kind of tilt one of the magnets, the electron comes through, gets polarized by the first one, and as it interacts with the second one, it will cause it to flip back. And this is just a conservation of momentum. So this is called a spin transfer torque, and it's very nice, and it's just being put into devices now, but they're very expensive, and they also waste a lot of heat, and so now people are trying to think of better ways to do this. And the other thing is that every time you have this electron go through, you only have this spin 1/2 particle that gives momentum. And so through the talk, I will show you a way to actually do it in a much more efficient way. But let's continue with this idea of spintronics. And so one of the big things in transport of spintronics is called the spin Hall effect. And what happens is as you send a current through a normal metal, say something like platinum, what will happen is the spins will split from the up spins and down spins will split and go to the side of the material. And this is probably one of the most fundamental aspects of spintronics in studying materials. And the ideas of this comes from several different areas. So one of it comes from relativistic physics, where you have, when you have high speeds and very large gravitational pull, then you have this idea of Dirac physics come in. I'll show you this later, and we also saw some of this Dirac physics in Aissa's talk. We also pull from ideas of nuclear physics, which I will show you later on, and we also pull from ideas of particle physics. So this is what we do is we take low energy expansions of our Hamiltonian and we get something that looks like particle physics. And so I like this field a lot because we can continue to combine all these things and that come from other fields of physics to get new physics in our field. And really quickly, I don't want to talk too much about this because it's a bit of a black box and causes a lot of explanation, but most of the work that I do is just this electronic structure theory and code called density functional theory, where you want to solve this Hamiltonian for a material, but you have billions and billions and billions of electrons. Instead of solving for each electron, what you do is you solve a mean field theory for all these interactions, and you act as this on this one electron and this electron density. And these are very complicated codes of millions and millions of lines and have been developed over the last 40 years. It also received the Nobel Prize in Chemistry in 1998, but we use a lot of the output for this code and the calculations to follow our calculations. So to continue, next I will go through pretty much of a general introduction of the field, and then I will jump into what's called these Berry phases of topological systems. And then I will talk about what's called non-equilibrium Green's function transport. And if we have time and no one's too tired, then I would talk about some of my results, which are not so important. Well, they're very important, but we can also discuss those after the talk if we don't have time. So continue. So let's start with something very, very simple. We start with a wave function that's a plane wave and has a periodic potential. And I think everyone understands that. And then you have, so this is a single electron and the Schrodinger equation where you have some kinetic energy and some potential. And you can say this potential has some structure, right? So in the case if you have a lattice, you can have something called a BCC lattice where you have a point in the middle and a point on four corners, and this lattice is periodic, so it repeats throughout space. You can also have something like an FCC lattice. And what you can do is, take this potential as it goes to zero, and then you have this kinetic energy term. And what happens is your energy states look something like this. So this energy states are a direct correlation between the crystal structure. So for BCC lattice, if anyone showed me this band structure, which is called a band structure, I would know this is BCC. And if they showed me an FCC band structure, I would know that's FCC. So what's very interesting about these is that they're all metallic. So what you can do is you can place your Fermi energy anywhere you want because you only have one electron. So you just fill it up and they don't interact. So if I put my Fermi energy here, there's always a state there. That means it's metallic. If there's no state, then that means it's insulating. And this is very important for the rest of the talk, so this is why I explain it. So just also remember that the crystal structure always has a very large impact on the band structure. And so the band structure is just the momentum space representation of the energy. So you're just plotting K for E in this case. To continue. So same periodic function. Now let's put an actual potential there in momentum space. This is the Fourier transform of the potential. And what this potential does is it opens up an energy gap on this band structure at the edge of the Brillouin zone. So this energy gap inside, if you put the Fermi energy, so Fermi energy refers to your Fermi-Dirac statistics where you're filling up levels due to the Fermi statistics, which is for electrons, you cannot occupy the same state with electrons. So here in the gap is an insulator. So this is something like glass, wood, all these things are insulators. And if it's not in the gap, then it's a metal. So this, what I would call right now, this gap is trivial. There's no topology involved with this gap. And the size of this gap is just based on the energy of the size of this gap is just based on the potential in this case. So to continue, you can do other types of potentials. But before we do this other types of potentials, we want to go back to what Aisha was talking about, and this is this Dirac equation she showed earlier. She showed something more like this, where she pulled out the MC squared, but here we have this Dirac equation, which is probably one of the most or more important equations in physics. And what this describes is the time evolution of it's not a wave function here, but it's actually a field here, sorry. So this is a field, and then you have your momentum and your mass term, your rest mass. Here, and this c is just the speed of light, and these are different types of matrices that will become more visible later in the talk. So what happens here is that you get the similar band gap that I showed you before, where it opens up, and the size of this band gap is 2mc. So this rest mass acts like a potential. Now the other part that I should talk about is So here you have these two cones, and does anyone know what these two cones are? So here is what's called positron on the bottom half, and on the top it's called an electron. So, but in each cone you have 2 electrons and 2 positrons with different spins. Now the size of this gap is very large, and so for me as a solid state physics, I deal with things that are on the order of 1 eV, 2 eV, 3 eV. The size of this gap is MeV, large MeV, what is it, mega eV, yeah? So most of everything I deal with is here, but we continue to the second part of the Dirac equation. So I get rid of the mass term completely, and now what I have is something that's linear momentum, which is this cone here. And so now I have 4 particles that touch at an energy gap, and this is shown here. And how all this business of topology and physics really got started was with this material called graphene. Graphene was discovered theoretically a very long time ago, but experimentally it was discovered in around 2004, where people took the pencils you have, stuck a piece of Scotch tape on it, and peeled off 1 layer of atoms, yeah? And so this is a very strong material. It bends. It's because it's actually completely transparent for 1 layer. For 2 layers, it becomes non-transparent. And this won Nobel Prize, but what's interesting about graphene is because of the crystal structure, you end up with a dispersion that looks just like this, which is a low energy dispersion. And so people said, okay, we can find something that's very similar to Dirac particles in a solid state system. And this is what kind of got this field going a lot. To continue, we go back to the Dirac equation, and we split this field vector into positrons and electrons, and you substitute your canonical momentum and your electric potential. And what happens is, if you expand this equation in terms of the velocity over the speed of light for very small velocity compared to speed of light, you get this term out. And this term, we get some other terms also, but I will not discuss those, but this term is very important to my work, and this term is called spin-orbit coupling. And if you remember from the first slide, what I was talking about is that we want to connect the spin to the orbit of the electron. So this term does exactly what we want, and it also brings all this physics of the Dirac physics and other physics, which I'll show you in the next slides. So that should be, sorry, small v, not small c. C is constant, this is the speed of light. So to go to these topological systems, what the spin-orbit coupling does is it actually inverts bands. So it acts on certain bands and not others. So for something like a symmetrical band, like an S band, which is just a sphere around the atom, it doesn't act on it. But you have something like a p orbital, which looks like a dumbbell shape, it acts on this, and it will invert the bands. And so what happens is it opens up a gap. And this was found right after graphene, but what happens is you open up a gap, and in the bulk of a material, you can have completely insulating, but only on the surface where you have a metallic state. And it's due to this Dirac-like point that you have that only shows up on the surface. And this is where the topology comes in from, because this material has a topological character that you can calculate from the band structure. Now you can go the other way, where you only open up a partial gap. And this is where you don't add too much spin-orbit coupling, but just enough. And so what happens is you get crossing points. And you get 2 types of crossing points. One is the Dirac point that I showed you earlier, and another is this wild point. And this picture's not so clear, but the next one will be. Sorry about that. So let's talk about the wild point. So this is the Dirac equation that I was talking about earlier. So now you have here 2 particles and 2 particles here with the mass term, and we set the mass goes to 0, so you have this crossing-like point. But now you can separate these 2 points into what's called 2 wild points. And the wild points, they both have this chirality, different chirality, and the integral of the directions of the spins in momentum space gives you this topological number. So for one, you get +1, and the other one you get -1. Total number is 0, but as you traverse through this momentum space, you get some charge that can actually give rise to new effects. And that's what people become very interesting about, is because these 2 wild points are always connected, and it's very hard to destroy them. So based on the symmetry of your system, you can break the symmetry of your system. So one way is to break inversion symmetry, or another way is to apply a magnetic field, which is breaking time reversal symmetry, or breaking parity in the case of the inversion case. And so what's nice about these wild points is that you have this spin chirality. So you get something that points in all directions, for different cases. And this is, in the beginning days before they were called wild points, they were called skyrmions. But now they're called wild points because there's a different name for skyrmions. And now I will tell you about skyrmions, which is very similar to wild points. But if you look at the equation here, you have something very similar, but instead of a momentum here, you have a magnetization. So a skyrmion is, from my point of view, is almost exactly the same as a wild point, but it exists in real space instead of momentum space. So now you just take the magnetic texture, and in the middle, it points down, and on the infinity, it points the opposite direction. And this is a topological object that you can move, and people become very interested in this because now you can make an object in your material and move it and detect it with electrical currents. And so you have many different types of skyrmions here. I show what's called a nil skyrmion, and this is a block skyrmion. And these are just projections into an SU2 sphere, and then this is just a rotation. But you also have other topological numbers. If you know about topology, you have 0, 1, 2, 3, and also you have the negative versions of this. And this here just tells you the winding of this topological object. But we can continue a little bit with skyrmions. So, as I said, I work a lot with experimentalists. So these are actual real experimental images. As prior, those were theoretical images of these skyrmions. And materials, this material here is called iron germanium. It breaks inversion symmetry, and because of the spinor recoupling, the spins are allowed to spiral, and when you apply a magnetic field, these skyrmions are stabilized. And people like this a lot because now you have a way to store information where these are about 70 nanometers. You can store information on a magnetic material that's much, much more dense than what we had before, where you're applying, as you have this disk, you have this reed head that applies a large magnetic field. And in these cases, they are made completely from electric field without any magnetic field. And people don't like magnetic fields so much for applications because they're very large and clumsy, and they kind of crosstalk between devices and kind of ruin it. So your device is too small, the magnetic field's not so great. But with an electric field, you have a lot much more control. So here it shows this device making skyrmions and blowing them and making different types of AND gates, OR gates, or NOR gates. And lastly, here is just the topological winding of this material. So to continue a little bit more, there's just some other materials I show that also show skyrmions, and just wanted to point out that the skyrmions are very thermodynamic properties. So they form usually at finite temperatures and under a magnetic field. So these are the phase diagrams as a function of temperature and magnetic field for different materials. And just by changing the chemical substituents, you can really change the size of this phase diagram. So this is what a lot of the work has been done in the last 10 or so years, and now people have a pretty good understanding of how to create the skyrmions, and now what we want to do is make the skyrmions as small as possible. So to continue. So now I want to go into this idea of topology, and this is this idea of what's called a Berry's phase. I believe in math it's called a Wilson loop. Is that correct, or anyone know? Okay. So this idea of a Berry's phase is here, which is here. If you think of it, if you have a pendulum at the North Pole and you traverse some path, a quarter of a path, and you come back, this pendulum will acquire some phase. In this phase, what you have is some potential that comes out, and this is called the Berry's connection. And you can just apply Stokes' theorem to get what's called the Berry's curvature. And this Berry's curvature is actually how we measure all of our properties. So what I do here is just rewrite this equation, but I write it in quite a weird way because I would like to use it more often. But so here you have some operator A and some operator B, which I haven't really defined, but what I can do is say this is an electric field, and this is my response to electric field. So this will be exactly this spin Hall effect that I see if I make this as a spin current here. And then if I want something like let's say if I apply electric field, then I can say, how does the magnetization respond to that? So this is a lot of what we do is we take this kind of equation and we just plug in different things and say, okay, hey, what kind of response do we expect from it? So you can, just by knowing this equation and the symmetry that you have, you can get a lot of information out of it. For one, I was saying the spin current, so you apply an electric field in this case, which is just a charge current. What happens is your spin split, which is the spin Hall effect I was talking about. But also you can look at that as the opposite of what's called the inverse spin Hall effect. So you input a spin current, Where a spin current has no charge, so it's very hard to read. Experimentalists don't like it. But if you input a spin current, you get a charge current out. So here was some of the first experiments done on this spin Hall effect about 2004, 2005, where people saw like in a material, gallium arsenide, I believe, where the red is spin up and the blue is spin down. You can actually see the spins separate here. And so far I have not told you anything that this is useful for, but here, so here is the spin orbit torques, which I will discuss more, but using the spin Hall effect, which is shown here, as the current split, you have a heavy metal here and what's called a magnet here. And as this spin goes through, it will cause a torque because they're misaligned. This will cause a torque in the magnetization, and you can switch to magnetization. And this also is another torque that happens purely at the interface where there's some change in the charge distribution. And the reason why I mentioned this here, because I showed you the spin transfer torque earlier where you have two different magnets misaligned. And there I said you only get the angular momentum of the electron. For this one, you actually get the whole angular momentum of the lattice. So it's almost limitless in this case of how much angular momentum you can give to the magnet here. Is there any questions? Okay.
Quick questions. What does SOT stand for?
Spin orbit torque.
And then ISHE?
Inverse spin Hall effect. Yeah, sorry. Yeah.
So why are you getting the angular momentum of the entire lattice in this approach?
It's directly due to the spin orbit coupling. So you're coupling because you have the splitting of spins from this lattice. Every time it goes up to hit it, it comes back down. It goes up to hit it again. Goes up again.
Is that like a container?
Oh no, this is just two different materials. So you have something like platinum and iron. Yeah. So you just make a hetero structure of two materials.
And does this generate heat?
Yes, it does. Yes. Yeah, almost everything generates heat in physics.
Right.
It's a good thing. It makes time go forward.
So basically you're testing materials that's in the hard drive and on particular devices?
I still have not gotten to my research yet because my research takes us a step further. But yeah. So I try to get to the background. This is quite new. So this is about 2014, and then in 2016 we proposed an idea that was a little further. So yeah, now I just kind of reiterate what's this spin Hall effect, which I was saying you can use to act on magnets. And what happens is with this spin Hall effect, when you have something like platinum, it's a non-magnetic material. So you have spins up and spins down that are equal in what's called the density of states. And with the band structure I showed earlier, it's exactly this density of states just summed over all k points with a delta function. And a magnetic material, what happens is you get a splitting of up and down states. And this, when you apply electric field, you get an actual voltage that goes across. And this is the Hall effect. If you guys ever took any physics courses, the anomalous Hall effect is one step further and it involves quantum mechanics and the inverse spin Hall effect, which I mentioned earlier. So most of it comes from this, but you can see it in magnetic materials and non-magnetic materials. To continue further, you have something what's called the Onsager reciprocal relations. So this is the relation between the spin Hall effect and the inverse spin Hall effect. If you apply a spin current, you get a charge current out. If you apply a charge current, you get a spin current out. But you can go a little further with this and say, hey, what if I apply a heat current? Will I get a charge current out? If you do, then you should get the opposite also. So this is exactly what you're saying. If you apply a heat current, if you apply a temperature gradient, then you get a charge current out. If you apply a charge current, you get a temperature gradient out. Temperature gradients are a little harder to measure, so people don't talk about it so much. So yeah, then you get all these effects, the spin Hall effect, you get the anomalous Hall effect, and physicists aren't so ingenuitive in creating new names, so we just change a couple of the words and call it the spin Nernst effect, the anomalous Nernst effect. And you can continue this whole idea of just, if I apply a charge current, what do I get out? If I apply a heat current, if I apply a spin, if I torque the magnetization, what do I get out? Most of those gray areas have been figured out already, but that's the main idea here that I wanted to show you. So to continue, you can also continue this even further and go into the quantum side of things. So let's go back actually to this Hall effect. So if you have just a regular metal and you apply a current, it usually just goes through and it's fine, but if you apply a magnetic field with it, the charges split, and this is just Lorentz force. Now, if you really, really crank up the magnetic field, like really, really crank up the magnetic field, what happens is these electrons that want to curve, or electrons or holes, will start to go into circular orbits, and these are called Landau levels. And what happens is when you fill your Landau levels at the right case, you get an edge current. And this is the beginning, also the beginning of this topology idea. This got the Nobel Prize in 1985, I believe. And what this looks like is when you fill these Landau levels, is you have some resistance that peaks at some point when you get to the edge of the Landau level, and then as soon as you go outside of the Landau level, it goes to zero. You have no resistance in your system, but you have a finite conductance that's transverse. And so this is kind of a weird thing. All your current that you put in comes out on the side, so it's completely displacentless. So physicists really love this because that means this system does not waste any heat in this case. It does in real systems, but theoretically it does not waste any heat. And so the same idea with the spin Hall and anomalous Hall, you can get these same ideas of the quantum spin Hall and then quantum anomalous Hall. I told you we're not very good at names, but so it's the same idea where the quantum Hall is just charge, the spin Hall is spin without a magnetic field, and the quantum anomalous Hall is one charge with one spin being circulated. This is probably the hardest one to do, actually, and it's the one that's been the most sought after right now in experiments. To continue, so a lot of these things are actually governed by symmetry, these responses. So you apply a current and you want to say which direction does this come out, and this is usually related to some symmetry tensor, which is directly related to the crystal, the size of the crystal and the crystal field. And so for here I just show a material that's a Heusler material, which I will go into more depth later, but to show that you have some crystals here, and the symmetry of this crystal will give you the symmetry of your response. To continue, I will skip this slide, I think, because I kind of, sorry. So to continue, what kind of theory do we use? We actually use a lot of different types of theory to calculate the transport properties. One is called the semi-classical approach. This is where you effectively add some perturbation into your system to get the electrons to scatter. I won't talk about that so much. There's a Kubel formalism, which I already talked about, and I'll show you another slide on it, but you've already saw the slide. And then there's a non-equilibrium Green's functions approach, which I will discuss in more detail. These are all transport types of calculations, but what you do is you usually take the Hamiltonian or the effective wave functions from some different other approximation, like this density functional theory or tight binding approximation, which I explained in the first two slides. Yeah. So this is exactly right here is the Kubel formalism, which I showed earlier. Which I use a lot to get just some simple information to know if these types of phenomena exist in the material or not. And now we will go into the non-equilibrium Green's function. So the idea of this is, it started, I think, in the 80s or so, when people first started wanting to build devices and things and understand devices. And what they wanted to do, because for a very long time, all we ever had was Ohm's law. And so you have this V equals IR. And this is kind of what's called a top-down approach, sorry. So this idea of taking everything from Ohm's law down to the microscopic level. And so what they wanted to do was have a theory that's completely from the microscopic level and build it up. And so there was a lot of restrictions on here because at the end it should reach Ohm's law. So the idea is that you have some region in between of some atoms that's what you call the scattering region. And so here you can put pretty much anything in here. And then what you have here is which are effectively called the leads. So this is exactly what you're doing is you're taking a battery and connecting it to the system. So putting a charge through. So what this yellow dot charge is saying that, okay, these leads continue on forever and they have infinite number of states. And this one has infinite number of states. And this one, so these two are semi-infinite and this one is finite, and so you're going to connect this system. This becomes a bit more of a more complicated numerical problem. But this idea can be related to what's called scattering theory, which I won't go into, and some people use, and I have used in the past also. It's this basic idea where you have a potential in the middle. This is a square wave potential, and you send in a plane wave. The plane wave gets reflected and also gets transmitted, and it comes through and That's the same idea, but now you want to do this all based on Green functions. And this is just the momentum of the plane wave. So yeah, so in terms of Green functions, you develop what's called the single particle Green functions, where you set it up for the left lead, the right lead, and the central region, and the connection between these leads. And you can set up the Green functions for all of these, but the main Green function you're interested in is this central region, this part that I showed here, this blue area, because you want to understand what kind of properties you have in this material. To continue, the Hamiltonian is very simple. Usually you have something that has these creation and annihilation operators. Is just the electron hopping from one site to the other. And then you have to get the self-energy of the leads to find out what the interaction this central region has with the leads. And this is just a very fundamental property of these types of calculation, is that connecting a device always causes some resistance, you know? So you always have some resistance when you connect this device, and that all comes in this, what's called the self-energy. To continue, so then you have, what people usually focus on in these calculations are the retarded Green's function, and this is just a step function, and you have your creation and annihilation operators, and then what I focus on a lot is called this G lesser function. And this G lesser function is not so well known, but what it does is it actually calculates the single particle current. So if you want to look at the current from a localized current between two sites, this is what you use. But what's nice about this operator is that it works exactly like this Kubo formula, the red formula I showed earlier, where all you do is just replace this. So already here, you have the particle current, the electric field application, and here you have whatever observable you want to read. So if you want to read the torque out, the temperature, the spin current, you just replace this and take the trace of it, and you have the result you want.
I can tell, okay, up there, the curly braces.
These ones?
Right.
Yeah, this is a commutation relation
Okay, like a
for electrons.
Poisson bracket or
No, it's a commutation relation, so it's just,
commutator.
Yeah.
Right.
yeah, yeah. Exactly, yeah. Okay, sorry. Continue, and are there any more questions, actually? So now, I mean, I take a sip of water, sorry. Yeah.
So what might be potential applications that you thought?
Oh, yeah, definitely, yes. So, I mean, for one thing is, you want material, so this graphene is a very nice material because it conducts electrons very easily. So there's a very high mobility of them because you have this free space for them to move. So if you use this kind of idea of the graphene and these kind of types of spin orbit torques, you can move the electrons very well, and then you can change the magnetization directions all by electrical means. But you can do this on a very small scale. So then that means your devices get a lot smaller in this case. So that's one application. I will show you some other applications with other materials also.
Something called the Internet of Things that maybe where they're looking at securing all of our devices, refrigeration, car, and this potentially could be an application. I don't know.
The Internet of Things? I don't know this, sorry, yeah.
Yeah, Internet of Things.
Okay, I have to look this up.
Like IoT devices like Nest, you know, like the thermometer, being digitizing it.
Well, yeah, I mean, so this, I think not so many people think of it for thermometer. A lot of times people think of this for heat conversion. So if you in your car, you generate a lot of heat. So you can use that waste energy to actually, if you put this waste energy into a device, then you can convert that directly to a current and use that again for your radio instead of wasting more gas in this case.
Are these type of measurements, like if you're doing like standards, like like basically equipment standards, like IEEE and stuff like that? Are these the type of processes that they go to in order to certify equipment to see if this is?
The only one that I know that you use in IEEE, and sorry, I go back. It's this quantum Hall effect, because this one, because it's a very precise measurement, and it tells you, I forgot, but I think it tells you like exactly the charge of an electron or something like this. So that's one of the things they use it for.
Because in order to certify a particular equipment,
Yeah.
or when you're doing some quality management or stuff like that, the requirements when you're putting your device together, like if Apple sends it
Yeah.
over, there's an expectation about when these transistors are touching other particular devices,
Yeah.
other components
Uh-huh.
and having that heat, and especially when you have the battery issue.
Yeah.
With Samsung and those.
Oh,
two
yeah, yeah.
areas. Because what happens is when you have a distributed, not your technology is not all done in house, but you have all these requirements all over the place. You have to follow a certain methodology with all of this, and then you bring it all together, and no one actually is saying the measurements on how does this all work together.
Oh,
You
yeah.
just basically bring all of these components together, and heat just happens, and then
It's not, yeah, it explodes, yeah.
explosion.
Yeah, another advantage of these spin-over torques I was talking about is that people do talk about the possibility of connecting both the memory and the processor in one device, and that would generate less heat and less communication. But this is, I think that's a much more of a complicated idea, which I have not really jumped on to so much. But
You had a couple questions. One, can you use this kind of technique for regenerative braking systems in a car where you take the heat from braking and turn it into electricity to charge the battery?
yeah, that's also the case, yes.
And then the other question I had,
But the thing is, you have to have a temperature gradient. So this is, I didn't talk so much about the temperature effects, but you always need a temperature gradient in the device. And you need two types of materials for temperature gradient. So I mean, theoretically, yeah, you can say something and you have some temperature gradient across, but to actually get the actual charge out, you need two materials, usually one with more electrons and one with less electrons.
so the other question was about can you perform addition and subtraction by controlling the spin orientation?
Yes, that's exactly quantum computing.
Yeah, exactly.
That's exactly quantum computing, yes.
You can do that.
Yes. But yeah, so quantum computing is so I talked about this topological insulator and then this Dirac particle and this Well particle, and there's one more called a Mariana particle. And this one is what they want to use for quantum computing because the particle is its own antiparticle. So you can do braiding and things like this with it and create different operations. But I didn't talk about that so much because it's also another big story. Yeah.
So you take these and connect it to like systems for sweat testing. You do this outside, and
I'm not an experimentalist. So I do everything in computation and things. So, yeah. But no, usually I think for an experimentalist, they are not so close to engineering. So a lot of the things they're doing at like 4 Kelvin. And if they do, I will show you a room temperature result, but they do it. It's usually in a very controlled environment. So they're not taking it outside yet or anything.
because when we were doing, I used to work in vehicle architecture,
Uh-huh.
something like B2B vehicle communication technology.
Yeah.
So we did a lot of sweat testing of devices.
Okay.
Using, there's a company, Southwest Research out of Texas, and we send the DOT will send them a device, and we'll have all of this equipment.
Oh, yeah.
Seeing the sun hit it, and then basically see when like the communication signals and see where they died down. Yeah, at a certain temperature. Or something.
Well, for most of the experimentalists, their devices are very they don't let me into the lab because I'm clumsy, and so they don't want anything to break. So it's very everything is very sensitive there. But yeah, so we can continue. Now I actually will talk a little bit more about the experimental part, where I was talking about this Hall effect. So what happens if you have a metal if you have a metal and you apply a magnetic field, what happens, the resistance response, this resistance that you have that's perpendicular to the current you apply, it's just linear in this case. And then if you go to a magnetic material, what happens in the magnetic material is you have different domains. So you have a bunch of domains and all the magnetization is oriented in different directions, and as you apply a magnetic field, you start to align all these domains, and all these domains want to point in the same direction. And this is exactly the experimental curve you should get for most materials. You get this anomalous Hall effect that comes out. And then this is how they fit it for experimentally. And what's going into this is that you have a couple of things. In the semi-classical picture, you have this Kubel formula I was talking about, where you have this Berry curvature deflection, and then you have two other deflections that are, or scattering. You have something called like a side jump, where whenever this electron comes to a scatterer, it acquires an extra phase. And then you also have something that's like very similar to Mott scattering, which is where you see a scatterer and it's pretty like the normal type of scattering you would expect. So these two are a little different, and this one just scatters it to the side, left or right, depending on the spin. So to continue, what happened? What happened recently was that people would apply this magnetic field and they see this hump, and they did not know where that hump came from. And so this hump, so they said, okay, let's do this. Let's add these, let's fit these two and subtract and see what we get. And in the end, what they call it, this is this topological effect. And this comes from, this hump comes exactly from either these wild points or this skyrmion in this case. So just now that I just go over pictorially with you guys. So one, you have this Hall effect, right? In any material, it shows up. That's metallic or semiconducting. And then when you have a magnetic field with spin over coupling, you get anomalous Hall effect, which is this part that curved off. And then you have the spin Hall effect for materials that are non-magnetic and materials that are what's called anti-ferromagnetic. An anti-ferromagnetic material is the same as a magnetic material, but you have equal number of spins that point up and down. That would become interesting a little more later. And then what people saw is that, okay, hey, what if we have three spins that point out of the plane? This creates some cone that you can actually get anomalous Hall effect from that does not look like this one. So this one, they call it the a chiral ferromagnetic, and you can get this without spin over coupling. Yeah, go straight.
No,
I think we still have like 15 minutes, yeah.
I'm looking at that cone, the omega and stuff. Just want to understand that a little bit.
So this is just it's a cross product, or so it's just a chiral product in this case. So you have three spins, and you have literally S1 dot S2 cross S3. So it looks like this. Can everyone see this board over here? So yeah, you just have something like
the volume.
Yeah.
Three vectors. Parallel like that.
it's exactly that. So in this, what that does, it's exactly like the spin orbit term I showed earlier, where it was sigma dot del V cross the momentum. So it creates this term that's like spin orbit coupling that controls the direction of the spin, so you get this anomalous Hall effect. And then you can get the same idea for when they're flat in line. You get the spin Hall effect, which I showed, where it's just the spins that penetrate. And then lastly, it's this topological Hall effect, which purely comes from these skyrmions and different other types of magnetic textures. Everyone's okay so far? Is it too much or?
No.
Okay.
Okay.
Yeah.
That one right there.
This one or this one?
Yeah, the whole that.
Yeah. So.
Right there. You just went zoop. Just be a little slow on this one.
Okay. Yeah. No worries. No worries. Okay. So yeah. So this is the skyrmions, or these magnetic textures I was telling you about earlier. And this here is just if you take one of these skyrmions, a line across one of these skyrmions, and throughout your crystal, it just looks like this throughout. And if you apply a magnetic field, they all want to kind of rotate up, but not all the way. So they rotate throughout like this. And you get the same similar effect that you see here. But it's a little different because now you have, it's continuous. So you don't have this chiral product like here, but you have a continuous product. And I would go to, I think, this next slide. So yeah, so this is what the next slide is. So this is this chiral product I was saying that you have for this case, which just gives you this volume and acts like a source of spin over coupling. But in the case where you have very extended magnetic textures, you get something that's like this. So it's just a continuous chiral product. And this gives you your charge or your topological effect. So this for skyrmions is either 0, 1, 2, or -1, -2 in this case. So over this one, it's going to be -1. And what this does is it produces some effective field, some effective magnetic field or vector potential that acts on the trajectory of the electron and causes it to deflect.
And you can simulate that.
They actually see it in experiment, and I simulate it, yes.
For that triple product, you care more about the magnitude of it or just the sign of it?
Sorry?
Do you care more about the magnitude of the chi-ij
You care about the magnitude and the sign.
and the sign?
Yeah, so for different types of skyrmions and textures, it will change sign, yes.
The chi-ijk, the S dot, Si dotted into Sj cross K. When you go into the end term there, there's a space derivative, right? The magnetization relative to time, that actually should be that same equation, right? I would have thought it would have been m dot.
Yeah, so the thing here is that you have to go to the next space, lattice side.
So you displace it.
So this here is just a discrete derivative, yeah? So you have I plus 1,
Right.
yeah,
So the other one, you have actually stepping it in
Yeah.
from X and Y.
yeah. Yeah, so this is not so important, but it's called the Perel's phase. And so this all comes up into this, what's called this topological Hall resistivity, and it causes electrons to deflect. Let's see. Okay, I think I skipped this slide, it's not so important. Yeah, I just go back to, I like to reiterate some things. So in one case, I talked about where you have spin-orbit coupling and this magnetization, when you have everything in line, you have this anomalous Hall effect. So the electrons deflect left and right, and you get some voltage across. And this is what's called a momentum space barrier curvature. So this band structure has something in it that causes electrons to deflect, and then you get the anomalous Hall effect. So you do your integral and momentum space.
And so in the spin orbit coupling, that's LS coupling, right?
Yeah, it's just
It's just LS, it's just the interaction of the spin quantum number with the
angular momentum.
angular momentum.
Yeah.
And so in the expression you have there, where is the angular momentum term in the expression up top?
This one? Or the?
No, the H equal,
Oh no, so it's purely in this. This is just.
it's in that term.
Yeah, it's in the spin-orbit coupling term. So this is important because it splits the levels. When you have, it splits levels, and so then this is distinguished between one level and another level in this case. And then on the other side is you have this magnetization texture, which also splits the levels in a similar way. You have what's called a momentum space barrier curvature. So a lot of my PhD work was connecting these two and seeing if you make the magnetization texture stronger, how does the other one depend on it as you flip it and see what's in between. Yeah, so we continue. So then what happens when you connect these two ideas, and one of the things you get out of this is what's called the Delasinski-Mori interaction. And this is actually what causes the magnetization to rotate like this in the skyrmions. But it only happens in inversion broken symmetry, but you also get another term out of this, and this is purely due to now you're doing your Barry's phases and phase space. And the other term that you get out of this is called the spin. It's just this term that as you apply a current to it, spin orbit torque.
Torque.
Yeah, so this is what I was talking about earlier where you flip the magnetization, and as you apply a current, you're causing a force on this magnetization. And so what we saw from this is that you can actually do this, instead of having these heterostructures and things, you can do this all in one material. If you have the right material, you can apply the spin orbit torque. So now your devices become less complicated where you have only one material and you can apply the spin orbit torque.
Okay, go back to one slide, please.
Yeah.
No, the next one after that one.
This one, sorry.
You had one where you had 3 spins. One was a spin orbit coupling and 2 other spins. It's an image in the right corner after this one, I thought it was. Right there, yes.
Yeah.
So this one, so is that the only condition under which skyrmion comes into being?
No, there's a lot of conditions, but this is the one that is most seen experimentally.
Speaking specifically of the case here, we have spin 1, spin 2, and then this large spin orbit coupling term. So you.
Okay, no, this is one condition here.
That's one, but that's.
This is a different one.
Okay.
And then you can have one where it's all internally in the magnetization. So you can have it.
So it could be 3 spins, right? Or it could be 2 spins and a spin orbit.
No, because it's a link interaction, right? So it's like the Heisenberg. It works on the link between 2 spins.
But there has to be a third.
It has to be something that breaks the inversion symmetry.
Right, and that would be the SOC, the spin orbit coupling.
It could be, doesn't have to be. It could, I mean, the SOC could be all here. It's just you need something to break inversion symmetry. So in this case, you have this to break the inversion symmetry. In this case, what really breaks the inversion symmetry is the different materials.
Okay.
Okay? Yeah? Okay. Yeah, so then just to summarize, you have this topological Hall effect that happens in real space, this anomalous Hall effect in momentum space, and then what I was saying was you have this Delasinski-Mori interaction and the spin orbit torque. And the spin orbit torque, what we discussed earlier, you have two contributions to the spin orbit torque. So we have this two materials. You have a ferromagnetic like iron and something that's called a heavy metal like platinum because it has a lot of protons in it. It looks like a very large gravitational field when it causes this spin orbit coupling for the electrons. So you have this effect that happens at the interface that displaces the spins and acts as a magnetic field on the other case. And in the other case, you have this spin Hall effect that causes a torque on the magnetization. Now, so that happens, what I was saying, happens in bilayer systems. So you have to have something like platinum and something like iron. And the reason that happens is you break the inversion symmetry. So going from platinum to iron, you change the material. But you can do this internally in a material and create the spin orbit torque. And this is what we did in our work. And so what you have is something very similar to carbon is diamond, actually, in this case. Silicon in a diamond arrangement. You have this material, which is called it's a FCC lattice, but it's in a diamond structure. So you have two atoms, and what happens is as you apply a current, you get the spin polarization that points in opposite directions. And you can't really get any information out of the spin information because one points one way and one points the other way, and there's nothing to couple to. But if you decided to take one of these spins away or replace it with something else, such as in gallium arsenide, which is a very big material in devices, you can actually make use of this spin current. And so that's what we did. We took this material that's very similar to gallium arsenide called nickel manganese antimony. And this material has a magnetic moment, and because it breaks inversion symmetry, when you apply a current, you can actually torque the magnetization just in this material. And this is very, very similar to like a cat flipping itself. So as you apply the current, these electrons are like the tail that spins really fast as the cat falls, and then the magnetization, the body of the cat flips the other direction in this case. So it's all in one material you're doing this. So everything's intrinsic in this case. And for some reason, physicists like using cats as examples. We're not hurting cats. Yeah. So we did this. We worked on this with experimentalists, and they did this at room temperature, and they showed it. And we also applied several different theories to make sure it all worked. And this was published, I think, in 2016 in Nature Physics. To continue, so then we went further and we just showed that by changing the material, just changing the components of the materials, this is more the engineering aspect, changing the components of the materials, you can really increase the size or the efficiency of these spin orbit torques. And I have about 5 more minutes, so maybe I just discuss this and stop after the next 2 slides. So this is this previous material I was telling you about, this nickel manganese antimony. So all those previous results were used using this non-equilibrium Green's function. But so in this case we have ferromagnetics. They're very nice because everyone has known about them for a very long time. You can read them very easily, and that's what we use in most devices. And then you have this case of antiferromagnetics. And antiferromagnetics, I said earlier, that you have an equal number of spins that are up and an equal number of magnetic moments that are down. And so people have not liked antiferromagnetics for a very, very long time because they're very hard to detect and they're very hard to control. But with this spin orbit torque I was telling you about, you can control them. So it's really like you go in on an antiferromagnetic with little tiny magnetic fields and control it just by applying an electric field. So one of the first ones this was studied in was this called manganese 2 gold. And so manganese 2 gold overall has inversion symmetry. And I told you that you need inversion symmetry for the spin orbit torques. But if you look locally in the manganese 2 gold, each atom breaks inversion symmetry. And so this acts as different spin polarizations on each of them, which I was showing you in the silicon, and you can cause a spin orbit torque on this, and it rotates the magnetization very, very quickly because now with the antiferromagnetic, the coupling between them creates a mass center that you can use to control it. Okay. Oh, sorry. I thought I was trying to wrap it up. People have actually done this experimentally and put it into a device. So this is a switching of an antiferromagnetic going from a state of 1 to 0 with pulses, and this works on a terahertz scale. So this has become very interesting because now with with light pulses, you can control an antiferromagnetic and then read out the state. And this works at a very fast speed. But another reason for this application is that because antiferromagnetics are very resistant to external magnetic fields. So if you're, for instance, if you're in an airplane, you have these black boxes that use magnetics to store memory. An antiferromagnetic would not be disrupted by the Earth's magnetic field. They also use them in, for ocean research and other types of devices. And they're very, very stable, so they last. This is the purpose of this is to show that it's very, very stable. So it goes on for a very long time.
So you say you activate this with a light pulse? Is that what you said?
I did not put the experiment with the light pulse. This is only with electrical pulse, but you can do this with the ultra-fast light pulse.
And the light has to be circularly polarized, you know?
Yes.
So the M quantum number of the light interacts with the magnetic material.
Yeah, so it's a terahertz pulse. The only problem with that is that it's to read it, you still need to do it electrically. You can't read it optically.
But you're switching the spins back and forth, right? So you
Yeah.
should be able to see a change in the polarization of the light if you
Yeah.
as a technique for detection.
Yeah, it should be, yeah, but it doesn't penetrate all the way through. I think that's maybe the problem. Yeah, so I think I will end at that point because it's almost 3. That's 1 hour, right? Yeah. Are there any other questions? Yes.
I'm wondering if you could use something like this to initialize a quantum computer. Right, you want to set, after a computation, you want to reinitialize, sort of re-randomize things. Could you use something like this, you think?
These antiferromagnetics. I'm not sure actually. Yeah. I'm not so much into quantum computing, so I'm not exactly sure.
In present day, the technology that they use for quantum computing is usually squid devices. So you have a superconducting material, another superconducting material, and then there's like electron and a particle in a box, but instead of a particle, it's 2 particles. There's a Cooper pit that couples in between. And that's what most quantum computing devices based on today, not so much this technology.
Well, I was just wondering how you would implement something like that on a large scale to be able to do mass computation.
I mean, using this technology or using...
I don't know. I pick up a little bit from this talk because this is all new to me. But I'm just wondering, with something like this, you can control spins and things like that of atoms or electrons.
But
So I think maybe I understand your question. So I think the problem with that is if you want to control the spins, you have to change the direction. And the switching direction is much slower than the speed of the electrons. So that's the problem there is that you want the switching to be very, very fast. So I think a terahertz scale wouldn't be fast enough in this case to actually be applicable in this kind of that kind of device.
the device you show here actually is more akin to what he's saying. If you do it optically, you can actually switch the spins very fast.
Yeah.
Right?
But I think you would need something more than terahertz, right? That's what I was trying to say. Yeah, you need something much faster than terahertz, or maybe order of magnitude faster than terahertz. So at the moment, this is the fastest it gets is terahertz. So a lot of things. I mean, when you apply an optical pulse at a terahertz frequency, you're really like slamming the material already. So what happens is you cause the atoms to start to move and things like this, and you don't want to. In this case, you don't want that to happen. Yeah. Yeah, you don't want to, so you don't want to, what happens is when you apply a terahertz pulse, the magnetization, you want the magnetization to move, but not with the atom. So I think with Maurice's applications, he wants to have some phonons in there. You don't want any phonons in there, so you just want the spin to rotate in this case. Does that answer? And
You know, the question is poorly formed in my own mind, so I'm just kind of throwing something out.
On this graph, what's the difference in the red dots and the black dots?
it's the post direction, the direction of the post here. This is the red post and this is the black post.
Oh, okay.
So the switch, to show that it's switched.